You learn a lot by studying math. You learn a lot about other fields. One such thing here is there's been some dinosaur footprints discovered down, where is it at? At Dinosaur Valley State Park in Glen Rose, Texas. And, paleontologists have been studying dinosaurs for a long time. And where we can use math to help us understand a little bit about these things is based on their stride, how they move. Stride is the distance discovered from or measured from like a left foot to the next time the left foot hits the ground. And the distance between the two is called our stride. The distance between our left foot and our right foot, that's the pace. Now, these two maps right here, or these two illustrations, are very poor illustrations of dinosaur feet, but imagine with me. The one on the left, that's a meat eater. The one on the right is a plant eater. Notice that the pace of the plant eater appears to be a little bit more, well, their steps are wider apart as opposed to the meat eaters. Meat eaters' strides and feet are almost in line at 180 degrees. Not quite 180 degrees, but a little off. But however, the plant eater, their angle right there is a lot less, which means that maybe they don't need to move as quickly as maybe the meat eaters do. So how can trigonometry help us here? Well, what we're curious about is the pace angle in this particular case. But we don't have any of the angles. We are able to measure the pace and the strides on both of those, but none of the interior angles we are able to do. So therefore, the law of sines, which requires us to have at least an angle, can't be used here. So what do? Well, that's where we start to understand and look at an idea called the law of cosines. And that's something where we can use when we don't know three sides. So let's attempt to derive the law of cosines to see that it was something that actually can be proven. Take an oblique triangle and situate it in a coordinate plane such that one of the legs lines up along the x-axis. Just doing that to make sure to allow some points to be points or coordinates that are some easy coordinates to work with, such as 0, 0. This point over here is a length c and up 0, and this last point c is just some random x, y. From there, there's a couple observations we can make. We can identify the cosine of A as the adjacent over the hypotenuse, and the sine of A as the opposite over hypotenuse. I can solve both of those for its respective values, x. So x equals cosine A times B, or maybe I'll write it as x equals B times cosine A. And over here, y equals B times the sine of A. All right, let's just hold those for a little bit, but that allows me to rewrite x and y in terms of angles and sides. Now, I want to find this distance A right here, and how we can find that distance A is use the distance formula between points C and B. So if I have some A, that's going to equal the square root of x minus c squared plus the distance of y minus 0 squared. All right, that's just a distance formula. Let's square both sides. From there, we have an x and a y. Right now we have in terms of a and c's, x's and y's. Let's remove the x and the y by substituting in what we discovered earlier. X is b cosine A minus c, square all that, plus y, which is b sine A, all squared. All right, shake it loose. How you guys feeling all right? Feeling all right? All right, from here, let's square this entire term. So we have a squared equals b squared cosine A squared minus 2 times B times C times cosine A plus C squared. And then I have over here still the B sine A. I'm going to make that B squared sine squared. I can collect some of these terms here. So A squared, I'm going to associate the B squared cosine squared A next to the B squared sine squared A minus 2BC cosine A. All right, from here, I'm going to factor out a B squared. So that's a B squared left with a cosine squared A plus a sine squared A. I like that. I think I know where that's heading. That looks like that's just a 1, so I'll have an A squared equals B squared times 1 minus 2 times B times C times cosine A. And then from there, if I want to get A by itself, I take the square root of both sides. I want to see how they have that. So let's look at how we can derive the law of cosines. Take an oblique triangle situated on a coordinate plane here, and I situate it where one of the legs of the triangle is along the x-axis. Doing so kind of cleans up a couple of the points. So for example, one vertex is at 0, 0. Another vertex is at the point C, which is the length along the x-axis, 0. And then I have another point x, y. A couple of observations beforehand. I can take the cosine of A, which equals adjacent over hypotenuse, which is an x, over a b. And then the sine of A equals the hypotenuse, or the opposite, over the hypotenuse. Solving both of those, one for terms of x and one in terms of y, x equals, excuse me, got a little excited there, x equals b cosine A, and y equals b sine A. I wanted to rewrite my notations in terms of x's and y's. As one example, I'm going to solve for A in this particular case, and you'll see what happens here in a little bit. And so A is a distance formula between these points. I want to find out the distance or the length of A. And to do that, I can find the distance between those two set points. So the distance is A equals the square root of my x coordinates, the difference of my x coordinates, plus the difference of my y coordinates. All right, let's just start working that down. Notice I'm in terms of x and y's and sides, a's and b's. So ultimately, I want to get them all in terms of a common pair of variables, which will be, in this case, a's and c's. Let's square both sides. I have solved for x and y in terms of some trigonometric functions. So I'm going to rewrite it as a squared equals x is a b cosine A minus c, square all that, plus my y, I'm going to substitute that in for b sine of A, all that squared. All right, shake it out, work it through. Take a deep breath. A squared, multiply that out, so b cosine A minus c squared, that produces a b squared cosine squared A minus 2bc cosine A plus c squared. And then I deal with this one. That's a b squared sine squared A. I always love when I see cosine squareds and sine squareds. So let's see if I can get those next to each other. All right, I think I have all the terms in there. 1, 2, 3, 4 terms. 1, 2, 3, 4. Factor b squared out of this first one. Then what's left is the cosine squared A plus a sine squared A plus c squared minus 2bc cosine A. Cosine squared A plus sine squared A, one of our identities that we like. So I have a squared equals b squared times 1 plus c squared minus 2 times b times c times cosine A. And there we have one of our 3 potential law of cosines and the derivation of that. The other 2 you can derive in the same process, just looking for a different side. So let's use this now because we derived it. It's a tool that we have. Let's use that tool to solve some oblique triangles.